Hi everyone, and welcome to this talk, which will hopefully give you a bit of an idea of what deep learning is all about. My name is Jamie Kennedy, and I'm a final year financial math student in UCD. It's through my degree where I've really been introduced to the idea of data science and machine learning and things like that. I really enjoyed learning about it, so I've continued to learn about this stuff outside of college, such as doing a bit of work with a startup based in the area of artificial intelligence. I got to see how useful these skills are in the real world, so I'm hoping to share some of these ideas with you. Just a bit of a disclaimer before we start. I know some people here will have absolutely zero experience with data science, so the material might seem a little bit intimidating, but don't worry, everyone is the same when they're starting off. So, as you can see here on the slide, this event is being run by DataSoc. DataSoc is Ireland's first student data society, and our main goal is to sort of bridge the gap between industry and academia by providing students with opportunities to gain experience outside of the classroom. Just want to let you know that DataSoc is running another event next Tuesday, which is a Women in Tech event with Eileen Burns. Eileen is the head of legal tech and innovation at Arthur Cox. She works at the forefront of technological innovation and, in particular, the intersection between business and tech. So I think that'll be a good, interesting talk to go to. Also, I just want to make sure everyone knows that we run a blog on the website. This contains blogs on lots of different topics such as machine learning, data science and sports, algorithmic trading, and more. So, and if any of you enjoy writing blogs, you can also submit blogs to take that we can publish on the website as well. And now we'll get into the actual talk. So, the whole idea of this talk is I want to give you all sort of an introductory idea to what deep learning is and why we're hearing so much about it nowadays. And I'm then going to take you through a project which implements deep learning, and you'll have all the tools to recreate this project on your own, so you can throw it on your CV if you want. And this is just the structure we're going to follow. So I'll give you a bit of an introduction into the ideas, then I'll talk about the reasons for why it's so popular, explain a bit about neural networks, and then go through the project, and then I'll hang around at the end for anyone that has any questions. So what exactly is deep learning? I think this is a good visual to sort of give you an idea of where deep learning lies. It can consider to be a subset of machine learning. There's lots of different algorithms used in machine learning, and deep learning focuses on the use of artificial neural networks. Neural networks are designed to sort of imitate how humans think and learn. It gets the name deep learning from the deep neural networks, which have had many hidden layers of computation. So now just look at a couple of applications of deep learning. And the first picture you can see a self-driving car. Deep learning is the force that is bringing autonomous driving to life. Data from cameras, sensors, and geomapping can be used to train the models to navigate through traffic. Wimbledon 2018 also used deep learning to analyze hundreds of hours of footage of the tennis matches to auto-generate some highlights for TV. This saved them a ton of effort and costs. They're able to factor in audience response, player popularity, and more into the models to generate the best highlights. And possibly the most popular application of deep learning is in virtual assistants such as Siri and Alexa, like you can see there. Each interaction with these assistants provides them with a chance to learn more about you and your voice. Now let's look at a couple of the reasons for the rise in popularity of deep learning. So neural networks have been around since the mid 1900s, but for a long time they are considered as a pointless thing to research. It's only recent advancements in computing and the generation of huge amounts of data which have made them popular, as we're now able to train large neural networks unlike before. Another huge advancement is that we construct larger neural networks with more and more data. Their performance continues to increase as we add the data. This is generally different to other machine learning algorithms which reach a plateau performance. You can sort of see that in this graph here, how as the data increases, the performance of the deep learning algorithms just pass all the other algorithms. So now I just want to talk to you a little bit about how neural networks work. So you can see in this picture sort of what they look like, and we can see how they're split into three different parts. So you have the input layer, the hidden layers, and the output layer. I think the best way to see how they work is just to take an example. So suppose we want to use this neural network to decide if a person is a male or female. So then male or female will be the two output nodes, which you see on the right-hand side there. And the way we decide if they are male or female is by looking at three characteristics of a person. So it could be their height, weight, and hair length. So these three characteristics will be the inputs of the model that you can see on the left there. And then finally, we look at the hidden layers. Simply put, hidden layers are functions which turn our inputs into outputs. You're free to choose the number of nodes in your hidden layers, but be careful because if you have too many nodes, then the model would be too complex and could take too long to train, or just become too complicated. So now I'm just going to look at sort of how you train the model. So to train the neural network, the first thing you do is initialize it. So what this means is that you create random values for the weights and bias, which we can see here. The weights can be seen on each of the purple arrows. So each of the purple arrows. They show the strength of the connection between the two nodes which they are connecting. And then the bias can be seen in the green circles. We won't worry too much about that because the bias is a bit more of a technical definition. But it's basically there to account for any inputs which have value of 0. And then basically how it works, how like the sort of data moves from input to output, is say we take the top node in the hidden layer there, then you see the three arrows pointing at that. So you take the value of 1 from the top input and you multiply that by 0.01, which is the arrow connecting that input to the node. You then take the next input, which is 2, and you multiply that by 0.05, which is on its arrow. And then you take the final input, which is 3, and you multiply that by 0.09, which is on its arrow. And then you add up the three of these, and then you add the bias, which is in for the node in the hidden layer. And then this figure you get here, you can feed into the activation function to get your final output. And what the activation function is to introduce nonlinearity into the output of a neuron. And then you repeat this for all the nodes, and then you get your outputs. So now that we have our outputs, we perform back propagation, which is sort of the essence of neural network training. Back propagation compares our outputs to what the actual outputs are meant to be, and it finds the error rate. And then it moves back through the neural network, and it adjusts the values of the weight and bias to sort of reduce the error and make our outputs more accurate. And then it just keeps repeating this, and eventually the neural network ends up with values for weight and bias, which give us accurate output results. So I'll just pause here for a couple of questions if anyone has any. Is there any there? Oh, I have a few here. Yeah, I'll be sharing all the code after the talk, yeah. How many nodes would a real neural net have? It sort of really depends on the problem you're solving. So a good way to sort of do it is you take 2/3 of your input nodes, and then you add this to your output nodes. And that's basically just a good number for your nodes that is quite often used.
Also, there was a question from Jack William, if he could go back over the last word where you explain how the error gets reduced. Like I think it was the back propagation stuff.
Yeah, we go here. So can you see that there now?
Yeah, screen works now.
Okay, so what was Jack Whelan asking, do you know?
He was asking about, he said, could you go back over the last part there about how the error gets reduced?
Yeah, no problem. So basically, um, it looks at the output that we generate in the model, and then it compares that to what the output is actually meant to be. And then if you remember, we generated our output by combining the weight and bias into a function. So what it basically does is it changes the values for weight and bias to give the output of the function more like what the output is actually meant to be, and that will reduce the error. So hopefully that answers the question. Um, so yeah, I suppose we'll move on to the project now. So we'll go to Anaconda Navigator so we can create that virtual environment I was talking about. Um, so this is Anaconda Navigator here. It's a graphical user interface, including Anaconda, which allows you to sort of launch applications and easily manage packages and environments and stuff like that. So I'll show you how to create an environment here. It's pretty quick. So you just go over to environments here and you click that. And then you just want to go down here and create. So you can click create like that. And whatever you want to name your environment. And we want to create an environment in Python. Just a note though, for this project, I think it's better to use Python 3.7 instead of the updated version. I just don't think TensorFlow's working that well with the updated version at the moment. So click 3.7 and then create. I've already created one over here. And then in our environment, we're going to want to install the packages we need for this project. So the first package is TensorFlow. TensorFlow is an open source library for machine learning and deep neural network research that was developed in Google. It's very popular, however, it's not that easy to use. Because of this, we also want to install keras, which is a high-level API built on top of TensorFlow. It's extremely user-friendly and way easier to use than TensorFlow. It also allows us to quickly build neural networks without having to worry about some of the mathematical aspects, such as tensor algebra and stuff like that. So if you go to the environment which we just created, it might take just a couple of seconds to load up here down the bottom. And then we're going to want to install packages. So if you go up to here and you go not installed, because we want to see all the packages we haven't installed, and then you search whatever package it is you want to install. So TensorFlow, and you search it in there, and then you just click install, which I've already done. And we also want to install keras, which I talked about, so do that there. And then once you have that installed, you can look at installed and you can make sure you have them installed. So I'll just have a look here. And you can see I have the two of them there. So that means we're ready to go. So we can hop over to our Jupyter notebook and get going. So I'll just go over there. So we're in the Jupyter notebook now, and I've actually already written up all the code. So I'll just run through it. So the first thing we want to do is import the package we need, which is TensorFlow. So just to run a cell in Jupyter Notebook, it's just Shift plus Enter, like that. So we've imported the package now, and now we want to import the MNIST dataset. I'm going to flick over here to a website just so I can show you what that dataset actually looks like. So each of the images here represents an entry in the dataset. And if we look at an image in more detail, each image is made up of 28 times 28 pixels. So each image has 784 pixels in it. Any of the white pixels are stored as the number 0, and any of the darker pictures are stored as a higher number. So these number values correspond to the X values in our data. And then the label of each image is the Y value. So the Y value for the first one here is 0, then 1, then 2, and so on. So each image has 784 X values and 1 Y value. So I'll go back to Jupyter now, and I'll run that to import the data. So the MNIST dataset comes with the data already sectioned into training and testing data. So we just have to unpack it into these different sections. We do this because we use the training data to train the model, and then we want to see how the model will perform on data it hasn't seen before. So then we want to run it on the test data. So I've done that. And then we can print one of the X values here just to see what it actually looks like. So you can see here all them zeros, they'll correspond to the white pixels, and then these numbers here will correspond to the darker pixels. And then it might actually be clearer to actually plot these instead of just looking at them in their raw form. So if we do that, you can see that the pixels combine to form what looks like the number 5. So then we'll look at the Y label of that image to see if that is correct, which it is, yeah. So you can see that that is meant to be the number 5. So now we're going to want to normalize our data. We don't have to do this, but it's going to help our model train quicker. So it basically just changes all the values to be between 0 and 1. So I'll run that, and then we can print the entry again that we printed earlier, but now it has normalized values. So we can see what the difference is. So you can see all the zeros are still zeros, but then all the other numbers have now been changed to be between 0 and 1. So it basically just makes them sort of easier to handle. So now we're actually going to build a model. In this next part, there are some pretty technical bits that I will mention, but I don't want to get too much into the details because I'm conscious this is a beginner's workshop. So I'll just go ahead and build the model. So the first thing we do is define the model we want to build. So we are using a sequential model, and this is basically the simplest model, and it is a linear stack of layers. So I'll run that. And then we next define the input layer. We want to flatten this layer. This is because we have to reshape our tensor so that it can be used as an input for the dense layer. And once again, don't worry too much about that. And now we add our hidden layers. And we just add 2 of these to keep it pretty simple. We use dense layers here. A dense layer is sort of the regular deeply connected neural network layer, and it's the most common one to use. We also pass a couple of parameters here. So the first one is how many neurons are in the layer. So we have 128. The next parameter is the activation function, which you might remember we saw earlier when I was explaining neural networks. The one we use here is called ReLU, which stands for rectified linear. It's pretty much the default activation function, and basically it outputs a number directly if the number is positive, and otherwise it outputs 0. And then for the output layer, we have 10 nodes because we need each node to match a possible classification, and our classifications are just digits, so there'll be 10 of them. And then the activation function for this layer is softmax. Softmax is often used for the final layer of a neural network as it normalizes the output to a probability distribution, so it just makes it sort of easier to look at. Now we want to define some parameters to track while we train the data or train the model. So optimizer is the method used in neural networks to change the weights and bias to reduce loss. The atom optimizer is basically just the default. It's designed specifically for deep neural networks, and it kind of leverages the power of adaptive learning. Loss is basically the degree of error. So neural networks try to minimize loss, and we use sparse categorical entropy here because this is what you use for multi-class classification. If instead you just had a binary output, it would be better to use binary categorical cross entropy. And we also just want to track X3 just because we all know what X3 means. So now we just want to train our model on the training data. So we see X train, Y train there. And then we have defined it to run for 3 epochs. An epoch refers to sort of one cycle through the full training set. So we run the model for a few epochs to give the neural network a chance to see previous data again, to make sure the model isn't biased towards the last few data points. So if we run that now, we can see it now, it starts training through the epochs. So right now it's going through data for the first time, and it's sort of adjusting the weight and bias. And you see we get an accuracy of 0.92. So now it's going through the data for a second time, hopefully adjusting the weight and bias to make it more accurate, which it did. So up with 0.96, and now final time to run through the data, and you can see it improves again. So we have an accuracy of 0.9771 and a loss of 0.0717. So we're pretty happy with them because they're quite good results. So our model's been pretty accurate. But but now we want to check it on our test data, because everyone knows that neural networks are very good at training, so they're going to give good results on training data. But we want to make sure that they weren't overfit. So we want to make sure that our neural network actually recognizes sort of what makes different numbers. So what makes a 5 a 5, instead of just learning off the results from the training data. So we run it here on the test data, and we can see it's still giving good results with an accuracy of 0.96 and a loss of 0.09, which is quite close to the loss value on the training data. So basically, as long as there's not a huge difference here, you can be pretty happy with results. If there's a big difference, then it means your model was good on the training data, but it didn't adapt well to the loss data. So then it would have been overfitting. So that's pretty much everything I covered there. So I'll just share this again. And I'll just thank everyone for their time. And I'll just let you all know that I can hang around if anyone has any questions, but we've covered everything. So if anyone doesn't have any questions, they're free to leave as well. And thanks for coming. So if there's any questions, I'll be happy to answer them.
Well done, Jamie. Rajit just asked what version of TensorFlow you're using.
I can't remember. It's the most recent one that it also includes keras in it. So previously in the older versions, TensorFlow, you had to sort of use them separately, but because so many people were using them together, they basically just sort of worked keras into it. So that's why you didn't actually see me import keras into the Jupyter notebook there. Sorry, I can't remember the actual version though.
I had a question. So now that you've trained that model, could you theoretically draw your own numbers and run it through the model to classify them?
I could build on, not with right there, but I could build onto the model. And if I built like another GUI that allowed me to sort of draw numbers, then I could feed that data into the model. But that would require some more work. I think I'm opening up the chat here. Yeah, Alicia, I will be uploading the Jupyter notebook afterwards, so you can try along yourself. Can you see any more questions there, Sam?
Yeah, Rajit asked again, what would you usually save your models as, pickle files or something?
I just save my models in Jupyter Notebook because I use them. I'm not really sure what a pickle file is, so I can't really comment on that one myself. Anything else? No? So thanks everyone for coming. Hopefully you all learned a lot, and if you have any more questions, you can feel free to sort of message me or anything. And yeah, I think that's it. So thanks everyone.